If you came here expecting a tribute to classic rock legends, you may be in the wrong place. In an earlier Atoms episode, we explored the ideas of voltage, current, and power, and you might recall a particular animation from that lesson. There was just one issue. The source displayed was alternating current, AC, but the current shown behaved like direct current, DC. That mismatch gives us a great excuse to clearly sort out the difference between AC and DC. Let's start with the basics. DC, or direct current, describes a situation where electrons travel steadily in one direction. AC, or alternating current, means the flow of electrons periodically reverses direction. Here's where it can feel a bit confusing. When we say AC or DC, we're often referring not only to current, but also to voltage. So AC voltage and AC current both vary over time. DC voltage and DC current, on the other hand, remain steady. DC in action. Take a standard AA LR6 battery. It supplies about 1.5 volts. Imagine connecting it to a small DC motor like the kind inside a toy car. As soon as the battery completes the circuit, current flows in one consistent direction and the motor begins to spin. If we plotted voltage on a graph, voltage on the vertical axis, and time on the horizontal axis, we'd see a flat line. The voltage remains constant. Of course, no battery lasts forever. Over time, its energy depletes and the voltage gradually drops. Even though the voltage level changes as it drains, the polarity does not reverse. Polarity simply defines which direction is positive. In a battery, the positive terminal establishes the positive voltage reference. Now imagine flipping the battery around. The polarity reverses. That means the current flows the opposite way, and the motor spins in the opposite direction. AC in action. Now let's look at AC using a light bulb plugged into a North American wall outlet. When the switch is turned on, the behavior is quite different from the battery example. If we graph the voltage over time again, instead of a flat line, we see a wave that rises, falls, crosses zero, and then repeats in the opposite direction. As voltage increases toward its peak, current flows and the bulb grows brighter. After reaching that peak, the voltage decreases and the bulb dims. When the voltage hits zero, polarity flips. Current reverses direction. The voltage climbs toward another peak, now in the opposite polarity, and the bulb brightens again, then dims as it falls back toward zero. One complete rise and fall, positive and negative, is called a cycle. The speed at which these cycles repeat is called frequency, measured in hertz, meaning cycles per second. Depending on where you live, household electricity operates at 50 Hz or 60 Hz. That means the voltage completes 50 or 60 full cycles every second. Believe it or not, an incandescent bulb is technically flickering more than 50 times per second, but the change happens so quickly that our eyes perceive it as steady light. Bringing it all together. Although AC and DC literally refer to current, we use those terms to describe both voltage and current behavior. DC voltage remains constant over time. DC current flows in a single direction. AC voltage continuously changes magnitude and polarity. AC current alternates direction as the voltage switches polarity. So while DC delivers a steady push in one direction, AC keeps switching back and forth, rapidly and repeatedly. If anything here still seems unclear, feel free to ask.